Okay, welcome back. We're going to consider now the last of the independent variable types, and that's a continuous independent variable. So under the assumption that the logit is linear in the continuous variable, we have the model is beta naught plus beta 1 times x. The logit is beta naught plus beta 1 times x. And again, this is a very important assumption. We're assuming that the logit is linear in x, meaning that no matter what age I choose, if I choose an age of 20 or an age of 50 or an age of 80, it doesn't matter. If I want to see the log odds ratio, I'm going to use beta 1. Beta 1 is going to multiply, is the multiplier. And so I'm assuming that the log odds ratio stays constant over the entire range of age. That the odds ratio comparing a 20-year-old to a 19-year-old is the same as the log odds ratio comparing an 80-year-old to a 79-year-old. You know, that may in general not be true. I mean, especially with medical data, because, you know, as people get older, they have less physiologic reserve. And so the difference between a 19 and 20-year-old may not be very much. But the difference between an 80-year-old and a 79-year-old may be much more sizable. So this assumption that you have linearity in the logit is something that you really need to think about pretty clearly. You can't just make this assumption and think it's true. In our book, we have a lot of information, a lot of consideration about determining the scale of these continuous covariates. And the bottom line is that you have methods for testing whether linearity in the logit exists. And you should take advantage of looking at that. Don't simply assume that it holds, because it's a big assumption. Okay, so here we have the logit for someone whose value of x is x plus 1, which is just beta naught plus beta 1 times x plus 1, or just beta naught plus beta 1 x plus beta 1. And here's the logit for someone who has the next value of x. It's just beta naught plus beta 1 times x. So the logit difference is the logit for someone whose value of x is x plus 1 minus the logit for someone whose value is x, and that logit difference is beta 1. And that doesn't matter which value of x you chose. Now, most often, this value of 1 is not biologically very interesting. For example, would we really be interested in the odds for someone who's 1 year older than someone else? Probably not. That's a very small thing. We might be interested in what the effect of 5 years of age is, for example. Or would we be interested in the additional risk or the odds of 1 additional millimeter of mercury for systolic blood pressure? So somebody whose blood pressure is 1 millimeter of mercury larger than someone else? Probably not, because 1 millimeter of mercury, you can't even measure blood pressure that precisely. So just taking 1 millimeter of mercury makes very little sense. You might be interested in a 20 millimeter, you might be interested in knowing what the odds of someone whose blood pressure is 20 millimeters of mercury higher than someone else, but not 1 millimeter of mercury. How about cholesterol? I mean, would you be interested in 1 milligram per 100 milliliters of cholesterol, what the odds of someone whose cholesterol level is 1 millimeter higher than someone else? Probably not, again. So, you know, choosing the right multiplier is something that you can do that can help the readers of your paper. Taking 10 milligrams of cholesterol might make more sense than just 1. Or 20 millimeters of mercury might make more sense than just 1. Or 5 years of age may make more sense than just 1. In other instances, a change of 1 might be too much. So for example, if your variable was an index, and the index ranged from 0 to 1, a change of 0.1 would be, might be more meaningful, because 1 covers the whole range. So you'd want to have a smaller difference and talk about odds ratios there. So to develop a method for point and interval estimation for any arbitrary change of C units in the covariate, what we simply note again is that the log odds ratio for a change of C units in x is just the logit difference. The logit when x is x plus c as compared to the logit when x is equal to x. So the logit difference is c times beta 1. And the odds ratio is estimated as e to the c times beta 1. And so this is estimated, again, by running the logistic regression model and getting the estimate of the coefficient, and then multiplying it by c, and then exponentiating. The variance is c squared times the variance of beta hat 1, so that the standard error is simply c times the standard error. So all of this is easy, because now if you decide that you want a 10-year confidence interval, you take 10 times the coefficient for age plus or minus 1.96 times 10 times the standard error for age. And that will give you a confidence interval for the odds ratio, and you'll say that someone who's 10 years older than someone else, their odds is between such and such and such and such of greater odds of having the disease. Now the choice of C should be stated clearly in all the tables and all the calculations. And using rounded values are helpful. So saying to your reader, this is a 5-unit odds ratio, or this is a 10-unit odds ratio, is something that we really highly recommend. Keep in mind that all we're attempting to do with this is to provide the reader with a clear indication of how the risk of the outcome being present changes with the variable in question. Okay, so in the age and CHD example, the estimated logit was beta naught minus 5.31 plus beta 1.11 times age. And the estimated odds ratio for an increase of 10 years of age is just simply take e to the 10 times 0.11, and you get 3.03. Okay, and so that says that for every increase of 10 years of age, the odds of CHD goes up by 3.03 times. Okay? So that's a big statement, because again it says that it doesn't matter where you start. You can start at 10 years of age, difference between 10 and 20, or 80 years of age, difference between 80 and 90. You're saying that the odds is 3 times higher for the person who's 10 years older. Again, whether linearity in the logit holds, again, I'm just assuming it here. But whether it really holds is something that you really should test, and in our book we give you ways to do that. The 95% confidence interval for the odds ratio, you would take 10 times the coefficient, plus or minus 1.96 times 10 times the standard error. Okay, and so then you get a confidence interval of 1.9 to 4.86. Okay, so I hope that's clear. So at this point you can play with your homework assignment, again paying attention to the solutions, and after you're finished that, look forward to seeing you all in week 5.